MathSinger, yum!
Assume that there are 3 pieces of pizza available, and you are given the choice of either selecting both of the smaller pieces or selecting the one largest piece. Assuming you like pizza, which would you pick? Well, as we can see in this illustration, the largest piece of pizza has side length equal to the length of the hypotenuse of the displayed triangle, and each of the other 2 pieces of pizza have side length equal to the lengths of the other 2 sides. And so really this is a question about area. It's a question of whether or not the area of the largest piece of pizza is more or less than the sum of the areas of the 2 smaller pieces. Well, the area of a square is just the square of the length of its side. And so the area of the largest piece of pizza is the square of the hypotenuse. The other 2 pieces have areas s squared, the side length of the smaller side of the triangle, squared, and the medium slice pizza has area L squared, where L is the length of the long side. This probably looks familiar by now. What we're talking about is the Pythagorean Theorem. And of course, if you are a student of mathematics, you know that the square of the hypotenuse is equal, in fact, to the squares, the sum of the squares of the other 2 sides. And so, in this example, we have that h squared is equal to s squared plus L squared. And so it really doesn't matter which of the choices you selected. The largest piece of pizza is in fact the same size as the sum of the areas of the 2 smaller pieces of pizza. As the name of the theorem indicates, the Pythagorean theorem was known to the Greek mathematician Pythagoras, who lived from 570 to 490 BC. But the statement of the theorem was known long before that, thousands of years, in fact, before Pythagoras lived. And the first known proof was given by Euclid in his famous treatise, The Elements, the most important mathematics book that was ever written. It's likely that you're familiar with the Pythagorean theorem. You probably have heard it as a squared plus b squared equals c squared. But typically, whenever it's stated that way, it's not indicated specifically what a, b, and c represent. Of course, in that representation of the theorem, in that statement of the theorem, a and b are the lengths of the 2 smaller sides of a right triangle, and c is the length of the hypotenuse. I prefer to use s, l, and h because they're more meaningful: short, long, and hypotenuse. Short side of the right triangle, the long side, and the hypotenuse of the right triangle. You probably are familiar with this theorem, but it's also likely that you have never been shown why, in fact, it's true. I'd like to give several proofs of this theorem. There are literally hundreds, but I'd like to give you some of my very favorite ones. My very favorite proof of the Pythagorean theorem begins like this. We're going to take one copy of the triangle. We're going to put it, I don't know, maybe about here someplace. And I have 3 more congruent copies of this triangle, which we're going to place on the board. And we're going to place them so that they form a square. Like so. Now, whenever placed like this, the 4 copies of our triangle form one large square they also form a smaller square on the inside. And the smaller square, as you can see, has side length h. The side length is the side length of the square is the length of the hypotenuse of the triangle. And so the area of the, we'll call it the negative space, the space that's not made up of the triangles, right, but it's defined by the triangles, that space is, in fact, h squared. I'm going to shift the triangles a bit, and as I do, I'd like to remember the large square that was formed by these four triangles. So I'm going to outline it so that we remember where it was. And I want you to observe that as I shift the areas of the triangles, as I shift the triangles, the positions, the area of the negative space never changes. Of course, right? The negative space, that's the white space that makes up the center square. That area doesn't change as I shift the positions of the triangles. It moves where that white space is, but the area is still h squared all the time. I'm going to shift the triangles so that, well, let's see, I'll keep that one where it was, but I'm going to shift this one up here so that what I form here is a little rectangle up in the corner. And down here, I'm going to shift these triangles to form a yellow rectangle down in this corner. Now again, whenever I shift those triangles, the negative space, the white space, never changes. It's still h squared. However, in this configuration, what we can see is that the negative space actually forms two smaller squares, one with side length s, one with side length L. Well, the area of a square is just the square of its side length. And so this smaller square has area s squared. This larger square has area L squared. So the negative space, still being h squared, is also equal to, as we can see here, L squared plus s squared. And that is my very favorite proof of the Pythagorean theorem. Another clever proof of the Pythagorean theorem also uses four congruent copies of the same triangle with side lengths s, L, and hypotenuse h, except we arrange them in this manner this time. I should point out that because these triangles are congruent, the sums of the two acute angles add up to 90 degrees, and since the triangles are congruent, this angle that I'm pointing at here is equal to the angle up here, and so these two together form a 90-degree angle, which does in fact make this a square. So it's fair to say that the shape, the outer shape that we have formed with these four triangles is in fact a square, and it's a square whose side length is equal to the hypotenuse of the triangle. And so what we have is the area of the entire square, including the centerpiece, is h squared. But I can also express the area of the entire square, including the centerpiece, as, well, the sum of the areas of the triangles plus the area of that center squared. And so each of the triangles, has area, let's see, the area of a triangle is 1/2 times its base times its height. And so in this case, we have four copies of 1/2 times base L times height S And then I need to add in the area of the center square. Well, the center square is this side length squared, and this side length, if we can think about this for a moment, that is, well, it's all of L minus S. If I take the length of the base and I subtract off the length of the height, what I get is the length of that center square. And so L minus S is the side length of that square, so L minus S squared is in fact the area of that center squared. So the area of the entire yellow plus white square is both h squared as well as 4 1/2 LS plus the square of L minus S. Well, let's algebraically manipulate this just a little bit. This gives me that h squared is equal to, well, let's see, 4 times 1/2 is 2. And so this is 2 times L times S. And L minus S squared, if I expand that, what I get is L squared minus 2 times L times S plus S squared. Well, I think at this point you can see what's happening. We have 2 times L times S in this expression, but we also have negative 2 times L times S. Well, those two terms together form 0, and what we're left with is that h squared is equal to L squared plus S squared. Another proof of the Pythagorean theorem. The last proof of the Pythagorean theorem that I'd like to give today is actually a combination of the other two. We're going to use the large square that was formed by the four congruent triangles arranged so that the side length of the square is S plus L, and it's going to involve the other arrangement of those four congruent triangles that I have drawn inside. What we're going to focus on is the center white square, which has area h squared, because it is formed by the square that has side length h, the side length of the hypotenuse of each of our congruent triangles. Well, we can think of h squared in two different ways. We can think of it as the area of the large square of side length L plus S minus the area of the four congruent triangles, right? That would give us the area of the small square of side length h. We can also think of it as the area of the very small innermost square plus the area of the four congruent triangles. Well, let's start with start by expressing h squared as the large square of side length L plus S. So let's see, that would be a square whose area is L plus S quantity squared, and we're going to subtract off the areas of the four congruent triangles. So we'll subtract off 4 copies of 1/2 L times S, 1/2 base times height, right? So in that way we form the area of the square of side length h. We can also think of h squared as the area of the very small square in the center, and let's see, that side length was, well, let's see, this side length is all of L minus S. So that side length is L minus S, and so the area of that smallest square is L minus S quantity squared, and then in order to arrive at the rest of the square of side length h, we will add on the areas of the four congruent triangles. So we'll add on 4 times 1/2 times L times S. But what I'm going to do is I'm going to add these equations together. I'm going to add the left-hand sides together, and I'm going to add the right-hand sides together. Adding the left-hand sides together, of course, just gives me 2 copies of h squared. And whenever I add the 2 right-hand expressions together, what I have is, well, in the first one, I have a negative 2ls. In the second one, I have a positive 2ls. Those are going to sum to 0. And all I'm going to have left is the L plus S squared plus the L minus S squared. And if I expand those, what I've got is L squared plus 2ls plus S squared, right? That would be the L plus S quantity squared. And then I'm going to add to that the expansion of L minus S quantity squared. So L squared minus 2ls plus S squared. Well, just like in the last example, I now have a positive 2ls and a negative 2ls, which are going to sum to 0. And all I'm left with is 2 copies of L squared and 2 copies of S squared. So what I wind up with is 2 h squared is equal to 2L squared plus 2 S squared. Dividing both sides by 2 gives me exactly the Pythagorean theorem. We hope that this video has piqued your interest in the Pythagorean theorem, and we encourage you to investigate some of the many proofs that are available out there. Perhaps you'll even develop one of your own. For now, we'd like to thank you for visiting MathSinger, and we wish you well and look forward to seeing you in our next video. So long.